Hi everyone, this is Kalyan Kumar and welcome back to Chemistry Universe. We are doing a series on alkyl halides. We have covered 9 parts in that. You can check out all of them. I'll put the link of each of the videos in the description below. And this is going to be part number 10. And in this one, we're going to talk about SNi and SNGP. We've done SN1, we've done SN2. In elimination, we've done E1, E2, we've done EI, we have done even CB. And in substitution, we have done SN1, SN2. And today, it's the last of the 2 substitution reactions that we'll study, SNi and SNGP. So let's get the ball rolling and let's start with the video part number 10, SNi and SNGP. Now, in SNi and SNGP, the first thing that you need to understand is SNi. So, SNi stands for substitution nucleophilic internal. Now, what this basically means is that here the nucleophile and the substrate are the same molecule. In one sense, you can call it intramolecular, but we would prefer to call it substitution nucleophilic intramolecular. Definitely it is intramolecular because the nucleophile is a part of the same compound. The substrate has the nucleophile in itself. So that is why we call it SNi. SNi is a substitution reaction that occurs intramolecularly in which the nucleophile attacks the leaving group and the leaving group leaves in one step but from the same side. Now this is a key to this particular substitution. Remember here the attack of the nucleophile and the leaving of the leaving group is in the same step. It's a single step. But here the nucleophile and the leaving group are on the same side. The nucleophile attacks from the same side as the leaving group, unlike SN2 where it happened from the opposite side. So let's check that out. It is similar to SN2 in that the attack of the nucleophile and the departure of the leaving group occurs simultaneously, and it is different from SN2 in that both the nucleophile and the leaving group attack and leave respectively from the same side of the carbon. As I said, this is the key. They are from the same side. Now, to understand this, one of the best reactions to understand this is the conversion of an alcohol into an alkyl halide by using SOCl2, thionyl chloride, in the absence of pyridine. But then you have to first understand what happens when there is pyridine and how does the reaction occur and what does the absence of pyridine cause. The most common example of this type of substitution is the reaction between an alcohol and thionyl chloride in the absence of pyridine. And first, let's understand the reaction if pyridine is present here at all. So this is the alcohol. Okay, and as you can see, the carbon is chiral. And we reacted with SOCl2 and pyridine. And what do we get? We get Cl wherever there is OH. But it is inverted. It's pure SN2. Now let's understand how this is done. What is the mechanism? Well, in the first step, the lone pair, this alcohol has a lone pair, as you can see. So this lone pair attacks the sulfur of the thionyl chloride and the pi bond shifts to O. And you get an intermediate of this kind. And here, the proton gets transferred from this H to this O minus. That way, this minus goes off and this plus goes off. This is called intramolecular proton exchange. So, here you have this intramolecular proton exchange. And you get this one. Now, once you get this one, now what happens is the OH bond breaks and this bond comes here. The Cl will break and the Cl will attack this H. So let's see that this going here. Cl breaks, Cl takes the H and you get HCl. This is called chlorosulphite ester. It's the ester of a chlorosulphite compound. There could have been an H here. Instead of the H, you have some kind of an alkyl group here. So it's an ester. Now what happens is, now comes the role of pyridine. The pyridine attacks the sulfur with its lone pair. And again makes the pi bond go to O, because remember, pi bond is the easiest to break. Now once this happens, the O minus comes back and the Cl leaves because it's a good leaving group. And you get this. And now since you have a free Cl minus, the Cl minus now does SN2 on the carbon, on this carbon. So the Cl minus attacks this carbon and the bond between C and O becomes the bond between S and O, and the bond between S and N breaks in favor of N, and pyridine is lost again. So pyridine is actually acting as a catalyst. And what do you get? You get Cl attached from the opposite side, you get SO2 and you get pyridine back. So this is what happens when pyridine is present. And the advantage of this reaction is, now you must also understand that you must have done about percentage yield. Now what is percentage yield? Percentage yield is obviously the amount of product that you really get and the amount of product that you should have gotten had the reaction proceeded the way we write the reaction without any loss. But the fact is, we know that in reality you can never reach 100%. In fact, even if you can reach close to 60%, it's considered a very good yield. So one of the reasons why we get a poor yield is separation of the products. If we get more than one type of product, if the reaction gives you more than one type of product, you need to separate them in order to isolate them. So the separation, in the process of separation also, some product will be lost. So what will essentially happen is that you would always try to do a reaction in such a way that separation occurs on its own. And in this reaction, it occurs on its own. Because as you can notice, SO2 is a gas, it will simply go away. Now this pyridine that is present is going to react with this HCl formed and form pyridinium chloride, which will be soluble in the solvent. And the alkyl halide would dissolve, would sort of precipitate out, because alkyl halides are insoluble in polar solvents. And since we are using a polar solvent, pyridine will react with HCl, forming a ionic compound, a salt, which will dissolve. SO2 will evolve on its own and this will precipitate out. So luckily for us, all the three products are separating on their own. So this is a very good method for producing alkyl halides. And we will study this in alkyl halides in the preparation again. But now let's see what happens. Inversion of configuration, as you can see, attack at the backside SN2. Now in this method, all the products are naturally separated. SO2 is a gas, it escapes. HCl forms a salt with pyridine and is soluble, and alkyl halide precipitates out. Now let's see what happens when there is no pyridine. Obviously that step of pyridine attacking will not happen. So initial steps will remain the same. Cl2, the O attacks the sulfur and the pi bond goes to O, and the O attacks the sulfur. O attacks the sulfur and SOCl2, I'm sorry, SOCl2, and then the pi bond goes to O, then this O minus take this H, and eventually the OH bond goes and the Cl leaves, everything, all of that initial thing. In fact, let me show you what that initial thing is so that you can remember what we did. So this O minus picks up the H, and eventually the Cl takes the H and this comes to O, you get the chlorosulphite ester. So assume that the reaction is occurring the same way till the chlorosulphite ester, because it is only after that that pyridine is attacking. So we get the chlorosulphite ester. But since there is no pyridine, what happens is the Cl of this SOCl2, the one of the Cls left, will attack this carbon from the same side, and from the same side the O will leave, forming SO2. And now you will get a transition state like this, and eventually this will break into a compound with retention of configuration. So remember, in SNi we got retention of configuration. So stereochemistry, SNi produces a product with retention of configuration if the carbon is chiral in both the reactant and product, and the leaving group and nucleophile have the same priority on the chiral carbon. And if you look at kinetics, remember it is this single step which is the of course the alcohol and SOCl2. Yeah, the attack of the alcohol and SOCl2, that is what is the RDS. So in kinetics, the RDS is the attack of the alcohol on the thionyl chloride, and therefore it is going to be second order kinetics, as well as the molecularity will be 2. And if you were to talk about the factors that are affecting SNi, obviously the substrate is pretty important. But since, if you notice in the substrate, there was an intimate ion pair formed. If you look at this guy, can you see it is slightly ionic and the carbon has delta plus? So wherever this delta plus is stabilized, this will be formed much more easily. So what happens is that when it comes to substrate, SNi is formed by the formation of intimate ion pair. More stable the formation of a carbocation, more easily an ion pair can form. So it is tertiary, secondary, primary in terms of rate. And as far as solvents is concerned, more polar the solvent, better are the chance of SNi, because the intimate ion pair will easily form. So that ends up with our SNi. Now let's talk about SNGP. And this is really, really interesting. Now SNGP is substitution nucleophilic NGP. You know, S substitution, and it is always nucleophilic. NGP stands for neighboring group participation, which means the group that is generally beta to the leaving group tends to make the reaction go faster than otherwise, as well as it helps retain the configuration on the carbon rather than what would happen if it were pure SN2. Let me explain. So there are some nucleophilic substitution reactions which occur at unexpectedly higher rate due to the presence of a nucleophilic group at generally the beta position. Say for example, I've got this. Now this is the leaving group. Now ideally, if an SN2 were to happen, the nucleophile will attack here and the leaving group will leave. Or if it were SN1, the leaving group will leave and carbocation is formed, then the nucleophile will attack. But here what happens is, this is the carbon alpha to the leaving group, this is the carbon beta to the leaving group, and that has a group which has a lone pair, which is therefore nucleophilic. Now this would first attack this carbon from the back side, and then the leaving group leaves. And you get this, an intermediate. It's not a transition state, it's an intermediate, it's real. Now the nucleophile comes, and let's say it attacks the same carbon, the one with R3, R4. Let's say it attacks this carbon only. So in which side will it attack? The Z attacked from the back side of the leaving group. So this will attack from the back side of Z, which will again become the same side of leaving group. So the nucleophile attacks here, the Z leaves, and you get this. Now, even though technically speaking, the product looks very similar to what the product would have looked had the nucleophile simply substituted the leaving group. Nothing changed. Instead of leaving group, now you have a nucleophile. The difference happens when you look at the chirality, when you look at the configuration of the carbon. So now this is SN2 and this is RDS. This is also SN2 and this is RDS, the first step, the attack of the neighboring group. So now let's look at examples of SNGP. real examples, and where I'll give you each element acting as a neighboring group. So first comes sulfur as a leaving group, as a neighboring group, sorry. So this is a compound. Br is the leaving group. Sulfur, as you can see, is in the beta position. Now generally it is beta, not always necessary. This sulfur, remember the sulfur and the Br have to be oriented anticoplanar. Only then the first SN2 will happen. And the reason there is retention here is because two SN2s are happening simultaneously. So this sulfur would attack carbon and the Br would leave. Now one might ask, why not the OH minus is attacking before the sulfur does? Because remember, intramolecular reactions are faster than intermolecular reactions because the distances are smaller. So you get this, and then the OH minus attacks. It is the only option of coming from the rear side, and you get the product. And now you can find the difference. You can know whether it is SNGP or simply simple nucleophilic substitution, even though the carbons are achiral before and after, by labeling a carbon with C14. Let's say the leaving group is present on the C14 carbon. Now, if it were a direct nucleophilic attack on this, the nucleophile will also be present on the C14 carbon. But look what happens. You get this? Now the nucleophile can attack either of the two carbons. Now if the nucleophile attacks the C14, it will be present on C14. But if the nucleophile were to attack on the other one, look what happens. Can you see? This clearly proves there is a neighboring group participation. Let's check out halogen as a neighboring group, and both are 50% here. Halogen as a neighboring group. Well, I got this. And OMS, if you go, you can understand mesylate, good living group. I is opposite to it, attacks, OMS leaves. You get this 3-membered ring. The nucleophile attacks, backside, and you get this. Let's see benzene. Benzene can also act as a neighboring group. You just need to have a group that is electron rich. So the pi electron of benzene moves here. It attacks this carbon. This leaves. You get the 3-membered. The nucleophile comes, attacks this carbon. This sigma bond shifts to form the pi bond. And you get this. You can have obviously olefinic double bond. If benzene can act, definitely olefinic double bond can act. So this attacks this carbon, Cl leaves. You get this, nucleophile comes, attacks this carbon, this bond goes back, and you get the product. And finally, nitrogen as a leaving group. And in nitrogen acting as a leaving group, you need this. And here the same process happens. And if you look at the stereochemistry, assuming both carbons were chiral before and after the attack, that means the carbon having the leaving group was chiral. The carbon now having a nucleophile is chiral, and the leaving group and the nucleophile have the same priority, then the carbon will show retention of configuration. So if the nucleophile attacks the same carbon from which the leaving group leaves, and the carbon is chiral before and after the attack, and the nucleophile leaving group have the same priority on the chiral carbon, then in SNGP, there is retention of configuration. And if you look at reaction kinetics, I already told you it is the attack of the NGP that makes the RDS, and therefore it is unimolecular with first order kinetics. So let's do a couple of questions. In how many of these is NGP possible? So as is the normal routine here, I'll give you this. Take your time, pause the video. I'll give the numbers 1, 2, 3, 4, 5, 6, 7 of these. Now pause the video. On your own, try to find out which of these will show NGP and then look for the answer. Then play the video back. Now the SNGP will occur in 1, 3, 4, 5, 7. 1 because of the sulfur. Now you are going to wonder why not 2? 2 also has a sulfur with a lone pair. But remember, this and this have to be opposite because this is the leaving group. Unless and until the leaving group is opposite to the neighboring group, it's not going to leave. And in a ring, you know, a single bond rotation is frozen. It doesn't happen. Now, 3 is expected. There is no ring here. It can easily do it. 4 can happen the same way. It need not be beta always. And this 5 also can happen, because this O minus will attack this carbon and the Br will leave. And 7 can happen, very simple. OT is a good leaving group, the pi bond comes and, you know, makes it. But here it won't happen because the O minus and I are on the same side. They're both on top. They're not opposite. So it's not going to happen. So make sure that you understand that. So now compare the rate of hydrolysis, that means reaction with water to form an alcohol, of these two alkyl halides. Now first of all, find out which will have NGP. Obviously, the first one. And the one with the NGP is always faster. So 1 is more than 2. And if you want to look at the order, it is 70,000 versus 1. And let's take 2 more examples. Try to find out where NGP occurs most. Order. Pause. Work out the problem and then play. So obviously NGP occurs only in 3 because the double bond is opposite to this OTS. Here it is still, it's not going to do an NGP, but at least it will withdraw the electrons because of the electronegative sp2, and that will in turn make this into a delta plus. Whereas it will not happen in 1, so it should be 3 to 1. And try these. Now obviously on the first glance you can see 3 is going to be the least, because no substitution on the bridgehead. Whereas if you look at the first and the second, the NGP is going to happen in the first one, because this is down and the sulfur is up. This is up, the sulfur is up, not NGP. And that gets us to the end of this video. So that sort of finishes off the part 10, SNi and SNGP. I hope this video helped you in understanding it. Watch it as many times as you want. If you have any questions, any queries, anything that you would like to ask, please drop them in the comment section below. If you like this video, please do give a thumbs up. And if you find such videos useful, try and subscribe to this channel and see if you like its content. And with that, this is Kalyan Kumar signing off. Have a wonderful and safe day. Goodbye, and I'll catch you in the next one.